Hi everyone. There are two approaches to defining probability: the classical and the Bayesian approach. In this video, we'll be talking about classical probability. Classical probability is also known as the frequentist or counting approach. Let's look at the following example. Consider the event of rolling an even number with a fair die. What is its probability? In the classical approach to probability, the probability of an event A is the size of outcomes in A divided by the size of the sample space. In our case, event A contains the outcomes 2, 4, and 6. And the sample space contains the numbers from 1 to 6, which gives us a probability of 3 divided by 6. Therefore, the probability of rolling an even number with a fair die has a probability of 0.5. In the video about terms of probability, the axioms of probability have been introduced. Let's quickly verify whether they are fulfilled or not. The first axiom is fulfilled as the probability of the null event is 0. No matter what we roll, no outcome is part of the null event. The second axiom is fulfilled as an event of A containing minimum of 0 elements or maximal the number of elements in the sample space. By dividing the number of elements in event A by the sample space, we get an inclusive probability between 0 and 1. The third axiom is fulfilled as for two mutually exclusive events, A and B, the event of rolling an outcome being in either A or B satisfies the probability of a union B is equal to the probability of A plus the probability of B. In general, for a random experiment with n equally likely outcomes, the probability of an event A with m out of n outcomes from the sample space is m divided by n. As you can imagine, counting all of the outcomes in an event and the sample space can be a lot of effort for complex experiments. Fortunately, we can use a principle called the multiplication principle of counting. If there are m ways of performing a task and n ways of performing another, then there are m times n ways of performing both tasks. Here's an example. Assume we're going to a cake shop, and we can choose 3 different shapes, 2 different fillings and 4 different toppings for your cake. How many different possibilities for cakes are there? Applying the multiplication principle of counting gives us 3 times 2 times 4, so 24 different possibilities. There are also 2 exceptional cases, namely permutations and combinations. Permutations are the different ways a set of elements can be arranged in a specific order. At the same time, combinations are the different ways a set of elements can be selected without regard to order. In other words, permutations consider the arrangement of elements, while combinations do not. Let's look at example for permutations. Assume you have 4 books that you would like to arrange on a shelf, and you would like to know the number of ways to arrange the books. We can take a random book from the 4 books and place it on the shelf. So for the first book, we had 4 possible books to choose from, and after placing it, we could choose from 3 books for the next one to place. We can repeat this until there are no books left, and we can see that we have 4 times, 3 times 2 times, so 24 ways of arranging the books. In a more general fashion, we have n faculty ways of arranging the books. An exclamation mark after a variable or number denotes faculties, and it translates to the formula faculty of n equals n times n minus 1 times n minus 2, and so on, all the way down to 1. Let's look at another example for permutations. Now we have 10 different books, but only 3 fit on the shelf. We have 10 choices for the first book, for the second, 9 choices and 8 choices for the third book. So the total number of arrangements is 10 times 9 times 8, so 720 arrangements. In general, if we only select k out of n options, there are faculty of n divided by faculty of n minus k possibilities. The other exceptional case is combinations. For example, assume there are 4 people, Alice, Bob, Claudia, and Daniel, at a party, and each person shakes hands with the rest. However, the order of the handshake does not matter, meaning it does not matter if Alice shakes hands with Bob or if Bob shakes hands with Alice. The handshake is the same. Therefore, we have 4 times 3 divided by 2 or 6 handshakes. In general, if we have n distinct objects, the number of choosing k of them is given by this formula. This part is read as n choose k. For the handshake example we get 4 choose 2 equaling the faculty of n divided by the faculty of n minus k times the faculty of k. This gives us the same result of 6.